Okay, let's look at relating tables, graphs, and equations today. This first slide should be a little bit of review for you. I want you to know that a function can be modeled with a rule. We usually call that an equation, a table, or a graph. When you're graphing, you always put your independent variable on the horizontal or the x-axis. So independent always goes with x. You graph the dependent variable, the one that relies on the other one, on the y-axis. Okay, so dependent, that goes on y, okay, on the vertical axis. And then what you're going to do is take the input and output values, and you can write them as ordered pairs and then plot your points. And then usually or often we end up joining the points with a line or smooth curve so we can have a general picture of the function. We like to see a pattern a lot of times. Okay, we don't always connect, but when we do, that's why we like to see it. Okay, so here's the first example. There's a few ways to do this, but right now we're just going to work on modeling the function rule y equals 1/3 x plus 2 using a table of values and a graph. Okay, so when I'm working on something like this, I like to pick some values for x. A lot of times, I mean, you're allowed to pick whatever you want, but I highly encourage you to pick some negative values, some positive values, and always include 0. I am going to pick multiples of 3 just because I know that I'm going to have to take a third of it, and I like working with whole numbers better, so it's your choice. But I'm going to pick for my x values -6, -3, 0, 3, and 6. It would be perfectly okay to do -2, -1, 0, 1, and 2. I'm just going to do it like this. Okay, when you're solving for y, you're just going to put in 1/3 times whatever x value you chose, in this case -6, plus 2, and solve out that equation for y. So y equals 1/3 of -6, that's -2 plus 2, that's 0. So we should have the point -6, 0 on our graph. When I do -3, same thing, I'd plug -3 in for x, 1/3 times -3 plus 2, so that's -1 plus 2, and that's 1. Okay, I'm going to probably just do most of the rest in my head. So 1/3 times 0 is 0, plus 2 is 2. 1/3 times 3 is 1, plus 2 is 3, and 1/3 times 6 is 2, plus 2 is 4. And now I'm going to graph these on my graph. And that only goes up to 5, so I'm going to plug -6 over a little bit. So -6, 0 is about right here. -3, 1, 0, 2, 3, 3, and 6, 4. I've got my line. Okay, that models y equals 1/3 x plus 2. And now I'm going to join it with a line, because this one is a straight line. Arrows on both ends, because that would keep on going forever in both directions. Okay. All right. So at the local video store, you can rent a video game for $3, and it costs you $5 a month for a membership to the store. Write a function to model the relationship between videos, v, and monthly cost, c of v. So another way just to say y or whatever, but c of v. Then make a table of values and graph. Okay, so first of all, what I need to figure out is how do these variables relate to each other. So it's $3 per video game plus $5 a month. And I'm just wanting to look at 1 month's cost. So it's just going to be that $5 fee. So I would probably say that c of v equals $3 per video game, so 3 times v, plus the $5 for the monthly fee. Okay, and then I'm going to make a table of values for this. Now, this time I don't want to pick negative values because I'm not going to rent negative video games. So my variables are c, v, and c of v. And I'm just going to pick whole numbers, maybe 0, 1, 2, 3. I would keep on going. If I don't rent any video games, I'm going to pay $5. 1, I'd pay 3 times 1 plus 5 is 8, and 11, 14, just going up and up. Okay, and you're going to want to pick a good scale and make your table of values. Now here I'm going to just be concerned about these values. So this is video game here, cost. Okay, and I'm probably going to go by ones here. 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm just going to try to make something smart happen. So if I run 10 video games, I'm going to do 3 times 10 plus 5. I know I have to get up to at least 35 here, so at least 35, and I have 10 spaces to do it. So I'm going to count by 4s, and I'm just going to show every other time. So I am really counting by 4s, I'm just showing the 8s every other time. Okay, and then I'm going to plot the videos, give it a title, video rentals or something like that. And just plot your points. So 0 is 5, and put in all the ones that you know, and it's going to keep on going up by a straight line. And I'll just put in a few of these. I know 10 is 35, so I'll put that one. I'll calculate 6. So 6 times 3 is 18 plus 5 is 23. That gives me enough points. Okay, and I could decide whether or not I want to connect these. Now, if you remember back in 7th grade, you're allowed to connect to see the pattern always, but let's go over some other reasons why when we connect and when we usually don't. So let's look at some vocab. You might have remembered that there were these two different types of data, and one of them was called continuous data. Data where numbers between any two data values have meaning. So you can have fractions of each, or I like to think of it as like something is always happening. If you look in between the points, something is going on. So if you look, not like does it go on forever, but is something always happening, like looking in between point 1 and 2, does that have meaning? Okay, so looking back at our last example with this video store, you would not rent like 1 2/3 videos or like, you know, any of these things that I'm writing with a red dot. Those would not have meaning. We don't have that amount of video rentals. So that's not continuous data. It doesn't have meaning. When it's just like the one before, we call that discrete data. Data that involves a count of each data. So things that are countable, like we could only buy 1, 2, 3, 4 videos or whatever. You don't have fractions of each typically. If that's happening, you do not usually connect the dots, except with this exception. Sometimes a solid line is used for discrete data if the scale makes it impractical to have individual dots. Like you don't want to draw 1,000,000 dots on there or something. So we might connect, or just times if you want to see a pattern, you're allowed to connect. Okay. So let's look at a couple and see what you think, if it's discrete or continuous. Determine whether the function rule model is discrete or continuous and tell me should you connect them. So at a ball game, they charge $2 per hot dog. Write a rule that compares hot dogs bought to money paid. Try this on your own, then check with me. Okay. So because I'm only going to buy whole numbers of hot dogs, 1, 2, 3, 4, etc., this is discrete data. Something's not always going on. Okay. If I'm going to write a function rule, I'll be fancy here. I'll call this H is my number of hot dogs. And I'm going to say M of H is my money. So I'm going to say my money, M of H, always equals 2 times the number of hot dogs that I buy. Okay, and that's my function rule. You could use different variables, that's fine. Okay, you drive 55 miles per hour on the highway. Write a rule that compares hours driven to miles traveled. So hey, I'm going to use H and M of H again. This time it's going to be miles and hours. And if I look at this, time is always passing, and the miles can be going by any number. There's like fractions of miles. You could drive 1.25 miles or pi miles. Something's always happening in between. So this is continuous data. And since I'm going 55 miles per every hour, I'm going to say that M of H equals 55 times H for my function rule. Okay. All right, sometimes you have to graph nonlinear functions. So nonlinear means it's not going to be a line. Graphing nonlinear functions are very similar to graphing linear functions. You can make a table of values. I like this method because it works for like all type of functions. You usually want to pick about 5 points for x and solve it for y and then plot your point. So let's graph this function, y equals absolute value of x plus 2. I'm going to make a small table up here in the top right. And I am going to pick some points for x. And it's really smart to pick some negatives and positives, always include 0. I'm going to pick -4, -2, 0, 2, and 4. Okay, -2, -1, 0, and 2 would be fine. So then I'm just going to solve this. So y equals absolute value of x plus 2. So I'll show the first one out by hand, but y equals the absolute value of -4 plus 2. So the absolute value of -4 is 4 plus 2 is 6. and then I'm going to do the rest mentally. Absolute value of negative 2 is 2, plus 2 is 4. Absolute value of 0 is 0, plus 2 is 2. Absolute value of 2 is 2, plus 2 is 4, and absolute value of 4 is 4, plus 2 is 6. So it's negative 4, 6. I'm going to go off the graph a little bit. Negative 2, 4, 0, 2, 2, 4, and 4, 6. So notice this is not a line. It actually ends up looking like a V. Absolute value graphs usually pretty much always look like a V. So if you don't get it looking like a V, you probably made a mistake somewhere and you want to recheck. Let's look at one that has an exponent. So y equals x squared minus 3. I want you to try this one on your own. See if you can do it. And I'm going to go ahead and try to work this one out too. Okay. So I'm going to try xy. I'm going to pick some values for x. Remember, negatives, positives, 0. I'll do negative 2, negative 1, 0, 1, 2 this time. Okay, so I'm going to always do x squared minus 3. So when you put in a number for x, you want to put it in parentheses. So I'm going to do negative 2 in parentheses squared minus 3. So negative 2 times negative 2 is 2. Negative 2 times negative 2 is 4. Minus 3 is 1. So I've got negative 2, 1. I'm going to put that on my graph. Negative 1 squared is 1. Minus 3 is negative 2. 0 squared is 0. Minus 3 is negative 3. 1 squared is 1. Minus 3 is negative 2. And 2 squared is 4. Minus 3 is 1. So I'm going to plot these points. Negative 2, 1. Negative 1, negative 2. 0, negative 3. 1, negative 2. And 2, 1. Now these look kind of close to a V, but you can see it's not actually going in a straight line. They end up really being U-shaped graphs, ones with those little squares. So I'd like you to try to connect that with more of a smooth curve. This shape, for future reference, is called parabola. If you tell me that tomorrow, I'll give you a chip. Okay, and it works with x squared. It's like when we have it's called a quadratic function. All right, a couple things to think about before we end. I want you to see if you can come up with some advantages and some disadvantages for function rules, for tables, and for graphs. I would love to hear some specific advantages and disadvantages when you come back into class. And I want you to be able to graph, make a table, and make a rule pretty fluently. Have a lovely evening.